Hello, in this section we're going to be looking at elastic energy. So essentially the energy that's within a spring or string, okay? Again, as a reminder, this is year 13 only. So if you're doing AS, you don't need to pay attention to this, okay? So elastic energy, okay. So firstly, I'm just going to play you a visual to help visualize what's going on here. Okay, so I've got this visual here, and so here simply got this ball on a spring, and it's just going up and down, up and down. It's being stretched and compressed and stretched and compressed. Okay, so hopefully you can see the movement there. Visualize that. So what's happening is, again, it's being stretched and compressed and vice versa. And so the energy in the spring is also fluctuating, okay? So the idea is the more stretched the spring is, the more energy there is involved. Likewise, as you compress it more and more, there's also going to be more energy as well, okay? And so that causes the ball to move up and down, okay? So hopefully that helps you see just clearly what the motion is looking like, okay? And if you want the link for that, if you want to test it yourself, feel free, there it is. But the essence you can see there is with movement, it stretches and compresses, right? And so the idea is there's energy involved in the spring or string. There's elastic energy, okay? And there's more energy the more you stretch or compress it, okay? So I'm going to say a spring or string possesses elastic energy as it is stretched or compressed, okay? And I'm also going to say if it's more, the more it is stretched or compressed, the greater the energy. Okay. Right. So again, you can also think of it like a rubber band. So the more you pull back on the rubber band and stretch it more and more, the more energy there is, right? The more it's going to flip, the greater it's going to fling forward, all right? So there's a lot more energy the further you stretch or compress a spring or string. That's essentially what we're talking about here, okay? So we're going to investigate exactly how to work out and deal with this elastic energy, okay? Now, it also turns out then, if we think back to work, right, from chapter 2, so work, energy and power. Work, if I remind you, work of a force is the energy to move a force, to move an object, right? A certain distance. Okay, so that's the whole idea of work of a force. We looked at that in the second chapter, which essentially tells us the energy to move an object to a certain distance. Okay, that's all it's saying. That's what work means. And so actually, it turns out that actually the elastic energy is the work of specifically the tension or the thrust force. Okay, so the elastic energy is basically equal to equivalent to the work done by the force in the string or spring. Specifically tension or thrust, right? Because that's the force in the spring. Okay. So there we are. Okay, so if elastic energy then is effectively the work done by the tension and thrust force, then can't we then say calculate the elastic energy by then calculating the work done by the force, right? So can't we just use the formula work is force times distance to work out the work of the tension force and therefore the elastic energy that way? Turns out no, we can't just use this formula to calculate the work, because this formula only works when the force is always constant, so it's always the same no matter what. Okay, so this formula is when it's constant force. So what I mean by that is, for example, let's say I have a little block here. Let's have a person pushing the block forward, right, with a force of 50 newtons, right? Let's say across 8 meters, let's say, right? Now the force is constant because it's always 50. So what I'm saying here is, for the entire 8 meters it moves, the person will always push by 50 newtons. But in reality, the force will change, because if you think, even let's say like working out in the gym or doing some physical work or physical activity, you're going to get tired, right, throughout, and especially towards the end, you're gonna have less force, right, because you're going to be tired. So the force naturally, in reality, should change and vary throughout the journey, right? So it turns out that the tension, the force in the spring then will also change. Okay, it's not going to be a constant force. Okay, well, we know that the force in the spring, so again, my tension thrust T here is lambda x over L. This is Hooke's law, you should be familiar with that. So if we look at this carefully, well, firstly, the modulus of elasticity does not change, right? A spring or string cannot change its modulus of elasticity. Likewise, it can't change its natural length. Those are fixed, okay? They will always be the same. But what can change is, of course, the extension or the compression, which is x, right? Because obviously, when a string, when they stretch more and more, it's going to have more extension, right? So therefore x will increase, x will change. And so what that also means, therefore, is the tension will change, okay? So therefore, for example, if a string stretches more and more, the tension will change and it will increase. So the idea is that actually the force in the spring, so a tension or thrust, that force will change, okay? Will not always be the same no matter what, okay? So I'm going to write down then, that T changes, or what we say varies more formally, the force T changes when X changes. Okay, and so in the context here, what I'm saying is, for example, tension changes when the extension changes, right? As a string is stretched. Okay, so hopefully you get that right. Hopefully you understand that that the force in the spring will change as it stretches or compresses. It's not always a fixed number. Okay, so what we need to come up with is sort of almost modify this equation, okay, when there's now a variable force. Okay, and so it turns out that when the force now varies, we can calculate the work of the force by an integral. It's going to be the integral between 0 and the distance travelled d, and I'm going to integrate the force, right, which is f of x. So my force is now a function. My force is f of x, and my distance is this d, right? It's my limit here. So what I'm effectively saying is, well, the force is f of x. It's a function. It's going to vary with x then, right? So the x here, that is what we call sort of the instantaneous distance. What that means is effectively, x is basically the distance we're currently at, okay? So again, let's have a look at this example here. Again, this person pushing a block forward. Obviously, it moves 8 meters in total. But what we could say is, if x is 1, let's say, if x is 1, then we're at the first meter, okay? Then when x is 2, we move 2 meters. X is 3, we move 3 meters. So what we can do is essentially work out the force at a particular point, okay? That's what we're basically saying, okay? And so that's what this x is doing. It tells me the point, so the distance I'm at in the journey, okay? And so there we are. And obviously d then, that's my overall, my final distance. Okay, to fully demonstrate this then, I'm gonna to fully demonstrate this, let's stick with this example, okay? So again, let's say we have 50 newtons pushing this thing forward, and the distance it moves is 8 meters, right? Now, it's a constant force, so we could say that work is force times distance. And so the force is 50 times distance 8, which is 400. That's great. But we can also work it out using the integral. And so the integral, well, it's going to be between 0 and the distance, which is 8, of my force. Now my force is just 50, so it's just going to be 50 lots of dx, okay? And so therefore we just work out this definite integral, think back to normal maths. So integrating 50, that gets me 50x between 8 and 0. And so if I just sub in these limits, I get 50 times 8, take away 50 times 0, which is just 50 times 8. And hopefully you recognise this is the same as force times distance, right? And so we get the same answer of 400, okay? So there we are. That's just how that sort of equation works, okay? So now we're going to use this to specifically then work out the work of the force in the spring then. So the work of this force T then. So the tension, for example. So the work of the force T then. So the work of T. Okay, well, let's set the scene. Okay, so let's say originally we have some spring, right? We have some string, right, at the natural length L, but then we stretch this string downwards like this. So it has still a natural length of L, but then has some extension, okay, which I'm going to say it's big X, okay? So hopefully you can see that, and that will cause a tension force to act upwards to oppose the downward stretch. Okay, so hopefully happy with that. So therefore, the work of the force in the string here, T, my tension, well, it's going to be the integral. Again, if we look here, it's going to be the integral between 0 and the distance travelled. Well, the total distance travelled is the extension. That's how far it moves down, right? So between 0 and big X of my force T then. But we know that also the force T, via Hooke's law, T is lambda X over L. So we can just sub it into the integral then, okay? dx, okay? And there we are. So now we could just work out this integral. Before we go any further, I just want to clarify the difference between these two x's here. So the big X and the little x. So the big X here, that is the final or the total extension, right? When we finish the stretching, okay? Now the little x in here is the extension throughout the stretching, okay? And so the little x will sort of increase from 0 when there's no extension towards the final extension x, okay? So x basically refers to the extensions throughout the stretching, okay? That makes any sense? Okay, so let's work out this integral. And that's going to be then between, well, firstly, let me rewrite, to make it really clear to see how we're going to integrate this. Let's say it's going to be lambda over L lots of X. And so now I need to integrate X here. So if I work this out, that's going to be lambda over L, which is just a number. Now, if I integrate X, that's going to be half of X squared. Okay, and so that's going to be between big X and 0. So now if I sub these limits in, that's going to be lambda over L lots of a half of big X squared, take away a half lots of 0 squared. And so that just simplifies to lambda over L lots of a half of X squared. Okay, big X squared. And so there we are. If I rewrite this then, that's going to be lambda big X squared over 2L. That should be an L here, not a 2. So 2L. And there we are. That is my expression for the work done, in the force in the string, so the tension. Okay. And so as we discussed then, the work done by the force in the string is the elastic energy in the string. So therefore I can now conclude that the elastic energy then we can calculate via this formula, which is lambda X squared over 2L. Okay, and there we are. Okay, that's the formula here. We also call the elastic energy more formally as elastic potential energy, or EPE for short. Okay, and there we are. So that's the formula here. So we're going to be using this formula to work out the elastic energy, the energy in a string. Okay, or spring. Okay, now I just want to clarify, I really want to emphasize, you do not need to know anything we've done here. The only thing you need to know from now is just this formula here. You only need to know the formula and to apply it to questions, which we'll do in a second. So if you struggled, or you're a bit concerned about any of this, if you didn't understand it or whatever, please do not worry. You do not need to know any of what I've done here. I've only done this to derive this formula for anyone who's interested, right? But you do not need to know how to get the formula. You do not need to know what I've done here. You just need to know the formula and how to use it. Okay, I just want to clarify that I've only done this to for anyone interested to see where the formula comes from. Okay, but yeah, so here's the formula then. So let's have a look at some questions. So firstly, we're going to just look at calculating this elastic energy, this EPE. Okay, so we've got this question here. So here we're told the elastic string, an elastic string that's natural length 1.4, modulus of elasticity 6. Find the energy stored in the string when the length is 1.6. Okay. Okay, but firstly it's asking for the energy stored. That's referring to the elastic energy in the string, which is the EPE. Okay. So the energy stored is the EPE, and that's going to be lambda X squared over 2L. Okay, that's just literally using the formula. Okay, again, you do need to know the formula. It's not in the formula book, but you'll pick it up once we do enough questions. Okay, so we just need to work out lambda X squared over 2L. That gets me my energy. Okay, now I know the natural length is 1.4. So what's happening is the length of the string is 1.6. So the original length is 1.4 and then it's extended to 1.6. Okay, so it's a stretch we're dealing with. So therefore the extension, that's going to be X, that how much it's extended by, well, that's going to be the 1.6 take away 1.4, which is 0.2. Okay, hopefully you're with me here. So there we are. So if the original length is 1.4, then it goes to 1.6. Clearly it's been extended by 0.2. Okay. So now we can work out this here. So therefore the EPE, well, the modulus of elasticity is 6 times by extension 0.2 squared divided by 2 lots of the natural length, which is 1.4. Okay, so if you work that out, that's going to be 0.086, and that would be in joules because it's a form of energy, right, to 3 decimal places. And there we are. Okay, so there we are. Hopefully happy with how the formula works then. I hope we just sub the numbers in, but there we are. Okay, now we've got this question here, fairly similar. Now it's asking for the work done. So the work done to stretch the spring. Okay, so the work done to the spring, well, as we sort of discussed in the start, that's going to be the same as the elastic energy. Okay, so the EPE. Okay, and we know how to work out the EPE, the elastic energy. That's going to be lambda x squared over 2L. Okay, so again, it's the same formula. Well, we know that the modulus of elasticity is 8. We need to find the extension x. Okay, well, we told the natural original length is 0.6, and then it goes to a length of 1, which means the extension is going to have to be 0.4, right? Okay. Again, that's because 1 take away 0.6 is 0.4. Okay, so that's the extension. That's how much it's gone up by the length. Okay, so then my extension is 0.4. Square that, divide by 2 lots of the natural length, which is 0.6. Work that out. And so then I get 1.067 again in joules, and there we are. That is the elastic energy, which is also then the work done to the spring. Okay, the work done to stretch the string, to stretch the spring forward. Okay, cool. Okay, now we've got this question here. So this one's going to be a bit more involved. We can't just sub numbers into the formula, unfortunately, here. So again, it's still asking for the energy stored. So that's going to be the EPE, right? The elastic energy. That's going to be, again, be lambda x squared over 2L. Okay. We know the natural length is 1.2. Modulus of elasticity is 10. But I can't work out the extension just yet. Okay. Again, so what we're going to have to do, good idea, draw a diagram. So what's happening is the particle is hanging down, so it's going to look like this. Okay, so I've got my spring, it's going to hang down with the particle in the end. Okay, so there we are. And so then we need to label what we know. So firstly, the forces. Well, the particle has mass 2, so it's going to have a weight of 2g downwards. And so then you can kind of see that the string is being stretched downwards. It's being pulled downwards by the particle. So therefore the force in the spring has to act the other way to oppose the downward stretch, okay, to oppose the stretching. And so that's my tension T. Okay, I also have a natural length of 1.2. So let's say the natural length goes up to there. So 1.2 here, and then and then we got our extension x. Okay. Now we can also use Hooke's law. So that's going to be T is lambda x over L. Please do not get this muddled up with the elastic energy, which is lambda x squared over 2L. This is Hooke's law, okay, which we've used plenty of times previously. Hopefully you're familiar with this. So okay, well, T is going to be lambda x over, well, again, the modulus of elasticity is 10. I still don't know my extension, and the natural length was 1.2, right? Okay, so in order to find x, I'm going to have to find the tension. But what I can also do, I'm told it's in equilibrium, which means no acceleration, which means if I was to resolve up and down, the forces have to be equal. So the tension acting up has to equal the downwards weight of 2g. So there we are, we've got T. So 2g, so 2 lots of 9.8, that's going to get me 19.6. Okay, and now we can substitute this into here to get x. So 19.6 for T is going to equal 10x over 1.2. Therefore 10x is going to be 23.52. Therefore x is going to be, if divided by 10, that would be 2.352. Okay, and there we are. So that's my extension, okay, which means my elastic energy, finally, we can work that out. So the modulus of elasticity is 10 times the extension, which was 2.352 squared, divided by 2 lots of the natural length, 1.2. So that would get me the energy to be 23.05 joules, and there we are. Okay, cool. Okay, we've got this question here. Again, it's the same situation. The particle hangs, so it's going to hang down. So again, it's going to look like this. Okay. Right, now I'm going to add my some stuff on. So firstly, my forces. The particle has mass 2m, so the weight of pulling it down is going to be 2mg, right? And so again, you can see the string is being stretched. We know it's being stretched for definite because the natural length is a, and then the length of the string is 3a. So it's going to look like this. So this is my natural length a. And so therefore it has to be stretched by a further 2a to get a total length of 3a. Okay, so it has to be stretched, which means the force in the string, the tension, has to act upwards to oppose the stretch downwards. Okay, so that's everything labelled. Okay, again, if I firstly resolve up and down, it's an equilibrium. So again, that means T has to equal 2mg. Okay, I'm going to leave it as that. Okay, and so then I can use Hooke's law. So that's going to be T is lambda x over L. Well, I know that T is 2mg. I know I don't have a modulus of elasticity. So that's going to be lambda times the extension. I do know my extension, it's 2a divided by L, which is the natural length a. Okay, well, actually the a's cancel here, top and bottom, so I'm left with 2mg is 2 lambda. Therefore, divide by 2, lambda is going to be just mg. Okay. Okay, so therefore then, my elastic energy, my EPE, is going to be lambda x squared over 2L. Okay, well, lambda is mg times my extension, which is 2a. That's going to be all squared, divided by the 2 lots of the natural length a. So if we just simplify this, so that's going to be 4a squared mg over 2a. And so we can cancel, we can simplify this, cancel it down. 4 divided by 2 is 2. A squared over a is a, lots of mg. Okay. And that is my answer. Okay, again, it's not an actual number. Don't be afraid. But that's the expression for the energy there. Okay. Okay, I just want to go over this question then because I think it's an interesting question. So I'm told here I have a light elastic string of modulus of elasticity 10, natural length 2. The string is attached to a fixed point A with a particle attached to the other end of the string. The particle is held at the point A. Write down the elastic energy of the string. Okay, so if I draw the scenario out here, well, again, I have a fixed point at the point A, and then obviously the string hangs down with a particle at the end of it here. But what I'm told is actually, quite interestingly, the particle is held at the point A. So actually, instead, the particle is literally at the fixed point. Okay, so the string is kind of like fully compressed in, pretty much, because if the natural length is 2, well, now the length goes to 0. So you might think that the compression, you might think it's a compression of 2 meters, right? And therefore you might say, well, the elastic energy, well, that's going to be lambda x squared over 2L, which would be 10 lots of x squared, which is the compression of 2 squared over 2 lots of 2. But that would not be correct. Why? And this is why it's interesting. I've got a string here. Okay, that matters because a string, if you remember, I think I made a very brief point at the start of this chapter, but one thing you need to know is with strings cannot be compressed. Only stretched. Okay, which means actually there's no stretching going on here. Okay, so actually there's no compression and there's no extension. Okay, so the extension is 0, which means if you were to use, if I was to calculate the elastic energy, then that would go to 10 of the modulus of elasticity, then the extension is 0. Okay, because the length is not greater than the natural length, right? So the original length is 2, and then the string is sort of pressed in. It's not been stretched, okay? And it can't be compressed because if you remember, because if you visualize a piece of string, if you sort of press into a string, it won't sort of shorten. It will go all loopy and floopy, right? So there's no extension here. It cannot be compressed. Strings cannot be compressed. So there's no extension. There's no stretching. Okay. So that means X then has to be 0 because the extension is 0. Okay. So very simply then, this will go to 0. Okay. So there is no elastic energy. Okay. And so that's why the question says write down the elastic energy, because actually I didn't really need to calculate anything. I could just see that, well, it's a string, and the string is less than the natural length, so it's not, so there's no extension, there's no stretching, so I can conclude that the elastic energy is 0 there. Okay, now if it was a spring, if it said spring instead of string, springs can be compressed. So if it was a spring, indeed the compression would be 2, and therefore it would be a different elastic energy. But I thought this was an interesting question to really illustrate the point that strings cannot be compressed. Okay, and so the extension here is 0. Right, now we're going to be looking at calculating a change in elastic energy. So very simply, that's the energy change between 2 points, essentially. So essentially the change in EPE is going to be the final EPE take away the initial EPE. So it's the difference between the elastic energy between 2 points. Okay, basically the same idea as the change in the kinetic energy, right? It's the same sort of idea. Okay, so let's demonstrate this with some examples. So here we're told an elastic spring has natural length 0.7, modulus of elasticity 20 from the work done, which means the elastic energy, EPE, the work done to the spring, so the EPE, when it's stretched from 0.7 to 0.9. So we've got this situation where the stretching is changing. So we've got these two sort of different points, right? These two different cases. So the first case is when the spring is stretched to 0.7. Okay, let's draw that out. Okay, so there we are. I'm not told there's any balls or particles, so I'm just going to leave it like that. Okay, it doesn't tell me anything at the end of it, but there we are. Okay, now so the length has to be 0.7. Okay, that's the length of the spring, but I'm told the natural length is 0.7. So actually there is actually no stretching or going on here, because this length here is the natural length, so there's nothing going on. Okay, so if I was to calculate the EPE here, this would be my initial EPE, because this is because we start at 0.7. Okay, so the initial EPE again is going to be lambda x squared over 2L. Well, my modulus of elasticity is 20. Now, times the extension, x, there is no extension because this is the natural length. There's no stretching going on. So that's going to be 0 over 2 lots of 0.7. Well, that just goes to 0, right? So there is no initial elastic energy. Then that makes sense, because if the string is at its natural length, it's not being stretched or compressed at all. So there wouldn't be any energy involved because there's no stretching or anything like that. So that actually makes sense, really. So then we're told now that the spring is stretched to 0.9. Okay, so it's going to be stretching a bit further down like this. So again, we're going to have a natural length, which is 0.7, but now the total length is 0.9 now, which means it has to be stretched by a further 0.2. Okay, hopefully happy with that. So now this will be my final EPE, because this is where it goes to. So that's again going to be lambda x squared over 2L. Okay, well, my modulus of elasticity is 20. Now the extension in this case is 0.2 all squared, divided by the natural length, which is 0.7. So 2 lots of 0.7. So that gets me that gets me the EPE here, the elastic energy, to be 4/7. 4/7, right? And there we are. Okay, so that's the idea, right? So we want to calculate the elastic energy, the EPE, between 2 points, right? So hopefully that made sense here. So therefore, the change in EPE, which should be the work done to stretch it from 0.7 to 0.9 meters. Well, again, that's going to be final EPE take away initial EPE. So that's going to be, well, the final is 4/7, take away 0 initially. Well, that's just 4/7 then, right? So there we are. Cool. Okay, now we've got this question here. So again, a similar sort of situation where we're changing the length, so it's being compressed to different lengths here. Okay, so again, let's draw these two different scenarios out. So firstly, it's compressed to 0.5, so let's draw that out. Okay, so there's my string. Okay, I'm told the natural length is 0.6, but then the length goes to 0.5, so this length here is 0.5. Okay, so therefore in this case, the compression, which is x, well, how much is it compressed by? So if the natural length is 0.6 and then it goes to 0.5, well, the compression has to be 1 at 0.1, right? Therefore, the elastic energy, the EPE in this case, which will be the initial EPE, Okay. Well, that's going to be lambda x squared over 2L. Well, my modulus of elasticity is 10. So that's going to be 10 lots of the compression, 0.1 all squared, over 2 lots of the natural length, which is 0.6. And so if we work that out, we get 1 over 12. Okay. And that's my EPE there. Okay. When the at this compression. Okay, so again, with compression, it works in the exact same, it works pretty much the same way as stretching. Okay, so we use the formula in the same sort of way. Okay, now I'm told the length of the string is now compressed to 0.3, so it's going to be even shorter now. Okay, so it's going to look a bit like that. Okay, so now my length is 0.3 meters here. So firstly then, again, my compression, in this case, well, again, the original natural length is 0.6, and now the length goes to 0.3. So the compression has to be 0.3, right? And there we are. So therefore, my EPE here, my final EPE, so the EPE at the final point here, that's going to be, again, lambda x squared over 2L. Okay, well, my modulus of elasticity is going to be 10 again. The compression, x is 0.3 here, all squared, divided by 2 lots of 0.6. And so if we work that out, we get 3 over 4. Okay, and that's my EPE at this stage. Okay, so therefore the change in EPE between these 2 points, between these 2 different compressions, well, that's going to be the final EPE, take away the initial EPE, okay, well, my final EPE is 3 over 4, take away the initial EPE of 1 over 12, so if we work that out, that's 2/3. Okay, and it's positive, which means it's a gain in energy. Okay, it's a gain in energy. Okay, and that makes sense because between these 2 strings, right, it's being the spring is being compressed even further, right? It's being compressed from 0.5 to 0.3, so a greater compression means there's more energy stored. Okay, there's more energy existing here. Okay, so it makes sense to be a gain in the elastic energy in the spring. Okay, hopefully that made sense. Okay, so it's very similar. We did look at an example like this, I think, in the first part of this chapter. And the idea is, well, firstly, my string is here. Okay, my string is here. It's from A to P. So you can imagine the string is being stretched downwards towards the particle, right? The particle is causing the string to stretch downwards towards it, which means the tension has to act up the string to oppose the downward stretch. Okay, hopefully that made sense. That's where the force will act. But also at P, obviously the particle is going to have a weight. Now the mass of the particle is 0.8, so it's going to be 0.8 g. Okay. Okay, but also what we need to do is, because now the string and the tension force is at an angle, it's at an angle 60, we're going to need to split it horizontally and vertically. So if you want to go up like this, well, if I do this, we can also go to the left here, then up here. Okay, so this component is going to be t sine 60, and this component is going to be t cos 60. Okay, again, this is sine, it's opposite the angle, so there we are. Okay, and cos here, because it's adjacent to the angle. Okay, there we are. So that's all the forces labelled. So we need to work out F, so let's resolve. So firstly, let's resolve forwards and backward to the right and left, right to the right and left. Well, my force to the right is F, and my force to the left is T sine 60. And there we are. Now they equal each other because it's in equilibrium. Okay, so the opposite forces equal one another here. Okay. We can actually simplify this because we know that sine 60 is root 3 over 2. And there we are. So we're going to need to find T. Okay. Okay, now you might be thinking I'll use Hooke's law, but we don't need to do that because if we also resolve up and down, it's a good idea to just resolve in both directions. So you don't miss anything out. So if we look up and down now, well, firstly, I've got my upwards force, which is T cos 60. That's going to equal the downwards force of 0.8 G. Well, there we are. We can work out T from this. We know that cos 60 is a half. So half T is 0.8 lots of 9.8 for G. So that means T, if I solve this, I get 15.68. And there we are. That's my tension force. So therefore my friction, not my friction, sorry, my force F, that's going to be root 3 over 2 times 15.68. And so that will be at 13.58. And there we are. That is F there. Okay. Cool. Okay, then in part B, it's now asking for the extension of the string. So that confirms indeed it's been stretched because it's asking for an extension. But there we are. Okay. The extension. Well, now we are going to use Hooke's law because we know what T is. Okay, thanks to part A. So that means T again is going to be lambda x over L. That's Hooke's law. So we know that T is 15.68. That's going to equal, well, lambda is 24 divided by the extension x, which we do want to find, over the natural length, which was at 1.2. Okay. So therefore we can solve for x here. So 24x is going to be at 18.816. So therefore x on its own is going to be 0.784, and that is my extension x. Okay, great. Then the final part is asking me to find the elastic energy. Okay, so we know that the elastic energy, EPE, that's going to be lambda x squared over 2L. Well, actually, this is quite nice because this is just plugging into the formula here, because we know the modulus of elasticity is 24. The extension we just worked out to be 0.784. Square that, divide by 2 lots of the natural length 1.2. So very nicely we can work out the EPE, the energy, to be at 6.15 joules. Okay, and that is my energy there. So we first need to find the tension in the string. Now, okay, tension. So again, you can imagine this is my string here, right, O to P. So it's again going to be stretching downwards towards P. So the tension is going to act up the string to oppose to stretching downwards. Okay, there we are. Right. So I need to add on. I need to consider my forces. Well, I know that's my tension. The particle is going to have a weight. Now the mass is m, so the weight is mg, acting downwards. But also again, because the tension's at an angle, specifically the angle theta. We're gonna have to add our own angle here. I'll call that angle theta. We're going to need to split it horizontally and vertically, so we could go to the left like this. This would be t sine theta, and then upwards, which would be t cos theta. Right, hopefully happy with that. And so let's get resolving. So let's firstly look up and down. Okay, well, my upwards force is t cos theta. That's going to equal the downwards force, which is mg. Okay. And again, they're equal because it's an equilibrium. Okay. I can also look right and left horizontally. My force on the right is this 5/4 mg. That's going to equal the left force of t sine theta. Okay. So actually, if you stare at these two equations, they're simultaneous, aren't they, really? In terms of t and theta, okay? M and g are just constants, okay? They're not variables we want to find, necessarily. We want to find t and theta, the tension and the angle theta. So if I write this out here, even more clearly, we have t sine theta is 5/4 mg. And also t cos theta is mg. Equation 1 and 2. So we need to find, preferably probably both of them, t and theta. I think the easiest one to start with is actually theta. Hopefully you can spot what we can do to these two equations to solve for theta. Hopefully you can spot we can divide them, right? So that'd be t sine theta divided by t cos theta would be 5/4 mg divided by mg. Well, the t's on the left cancels, and then we're left with sine over cos. Hopefully you recognise that comes to tan theta. That's my identity, right? Sine over cos is tan. And then the mg's cancel here as well. So quite nicely, tan theta is 5/4. Okay. Right, now we can find theta on its own if you want to, but remember what we like to do is actually consider a triangle, because we don't necessarily need theta here. We just need sine and cos theta. That will allow me to work out t. Okay, so if we just want to work out cos and sine, we can consider a triangle like this. Well, I know that tan theta is 5/4. I also know tan theta, due to SOHCAHTOA, is opposite over adjacent. So the opposite side must be 5 and the adjacent here is 4. If we do a bit of Pythagoras, the hypotenuse is going to be the root of 5 squared add 4 squared. And so that will be root 41. Okay, so root 41. Not particularly nice, but that's the reality here. So therefore, if we work out sine and cos of this triangle here, well, sine is opposite of a hypotenuse, so that's going to be 5/root 41. And cos is going to be 4/root 41, so the adjacent over the hypotenuse. Okay, so we've got exact values. Nice. So now we can deduce. Okay, well let's stick with this second equation here. So t cos theta is mg, but we know what cos theta is. Okay, we know that cos theta is 4/root 41. So therefore, t lots of 4/root 41 is mg. So t is going to be mg divided by 4/root 41. So divide that. Okay, well, remember with divided fractions, we keep flip change. So it's going to be mg times root 41/4. So that's going to be, well, just root 41/4 mg, right? Okay, and that's my tension. Okay, again, not particularly nice. Don't worry about the numbers or the letters. hopefully just understand the process is the same, the formulas and how we use it is going to be sort of the same. Okay, hopefully you're happy with this. So this is my tension, and there we are, that's part A done. That's the tension in the string. Okay, cool. Then in part B, then it's asking for the elastic energy in the string. So that's going to be the EPE, which is lambda x squared over 2L. Now the issue is I don't know what my extension x is. If I look at the question, I'm told the natural length is A, but I'm not told the total length. I'm not told what it's stretched to. I'm just told the natural length. I'm going to have to work out the extension then. But thanks to part A, I know what my tension is. And I also know, because of Hooke's law, that T is lambda x over L. So that means T, which is root 41 over 4 mg, that's going to equal lambda x over L, where lambda is 2 mg. Times x divided by the natural length, which was, I think, A. Yes, natural length A. And so at that point, we just solve for x. If I get rid of the fraction, so if I, firstly, if I multiply everything by 4, I get root 41 mg. It's going to equal 2 times 4, which is 8 mg x over A. Okay, then I can get rid of the second fraction by multiplying everything by A to then get root 41 AMG is going to equal 8 mgx. Hopefully that helps break it down to visualize what to do. So therefore we can divide by mg to both sides. So therefore I get root 41 lots of A is going to equal 8x. So therefore my extension x is going to be an root 41 over 8, because I'm divided by 8 lots of A. Okay, and there we are. That's my extension x. Okay, so now we can go back to working out the elastic potential energy, which is here. So EPE, well, the modulus of elasticity is again 2 mg times the extension x. Now x is root 41 over 8 lots of A, so it's going to be root 41 lots of 8 lots of A all squared over 2L, so it's going to be 2 lots of the natural length A. And then we just need to simplify this. Okay, so we need to simplify this fraction here. So that's going to be 2 mg lots of, well, if I break it down, that's going to be root 41 over 8 lots of A times by another root 41. If I get rid of this now. Okay, all divided by 2A. Okay, so if I expand sort of the top brackets, that's going to be 2 mg. So if I do root 41 over 8 times by another root 41 over 8, that's going to be 41 over 64. And so A times A is A squared. So that's there. So that's that. Okay, then I can, well, the 2's will cancel on the top and bottom, as will 1A. Okay, so A squared divided by A goes to A. So we just get 41 over 64 MGA. And that is my answer. Okay, that is my that's my expression for the elastic energy there. Okay, there we are. Okay, again, I think that's slightly tricky, final question there. I think mainly the algebra, but again, don't be put off by the algebra and the letters. Hopefully you saw that the sort of steps, the methods were kind of the same, right? But yeah, don't please don't freak out too much over the algebra here. Hopefully understood what's going on here. But there we are. Okay. So that's it. I'll see you next time.